Okay, let's start with a question. What could the phone in your pocket possibly have in common with a massive, room-sized supercomputer from the 1950s? I mean, on the surface, you'd think absolutely nothing, right? But it turns out they do. Almost every computer ever made is built on the same single secret blueprint. And today, we're going to pull back the curtain and see what it is. Just look at this. On one side, you've got this behemoth of wires and vacuum tubes, and on the other, a sleek, modern laptop you can tuck under your arm. They're separated by decades of just incredible innovation, yet, at their very core, they work in almost the exact same way. So, what is this secret connection? Well, the answer is something called the von Neumann architecture. Yeah, it's a design from way back in the 1940s. And believe it or not, this is the fundamental blueprint for pretty much all modern computers. You could say it's the ghost in every single machine. So for this explainer, we're going to take a tour inside the machine. Think of it like a guided walkthrough. We'll explore the four main rooms of the computer, starting with its memory, then checking out the brains of the operation and seeing how it all connects to the outside world. And then, at the end, we'll uncover the one big, brilliant idea that makes the whole thing tick. All right, first stop, let's get the lay of the land and look at the overall map of the machine. This is going to show us the main functional areas and, how they all talk to each other. So here it is, our map for the journey. Every single von Neumann machine has these core parts. You've got your main memory, a central processing unit, or CPU as we all know it, and the input-output gear that lets it talk to the world. Now, that CPU itself is actually split into two little sections, the program control unit and the arithmetic logic unit. And those are the four essential rooms we're going to visit today. First up is the memory, which is where all the information is stored. Then there's the ALU, which is basically the calculator. After that, the control unit, that's the manager. And finally, the I/O system, which handles all the communication. So let's dive in, starting with memory. Okay, I want you to imagine the computer's memory, its RAM, not as some tiny microchip, but as a giant library. A massive library just filled with millions and millions of tiny numbered mailboxes, and each one is holding a little piece of information. Now, there are two really important things you've got to know about RAM. First up, every single one of those little cells has a unique address. Think of it like a P.O. box number. That's how the computer can just zap straight to any piece of info it needs, instantly. The second thing, RAM is what we call volatile. That just means it needs power to remember anything. So you turn off the computer, poof, the whole library goes dark and every single one of those mailboxes is empty. So at this library, you can only really do two things. You can fetch and you can store. When you fetch information, you're just making a copy of what's inside a mailbox. The original data stays right where it is. But when you store information, you're putting a new value into a mailbox, and whatever was in there before, it's gone forever. This is a really key difference. Reading is non-destructive, but writing is totally destructive. So how on earth does the computer keep all this fetching and storing straight? Well, it uses two special little helpers, kind of like mail clerks. The first one is the Memory Address Register, or MAR. It holds the address of the specific mailbox the computer needs to visit. The second is the Memory Data Register, or MDR, and it holds the actual piece of data that's being sent or received. Every single memory operation, without exception, goes through these two. All right, next up, we're heading into the Central Processing Unit, the CPU. This is the true brain of the computer, and it contains the next two rooms on our tour, the manager, which is the control unit, and the calculator, which is the ALU. The control unit's entire job is to follow a recipe, a list of instructions that are stored in memory. And these instructions are written in machine language, which is the most basic language a computer can understand. Each command is incredibly simple, with just two parts. An opcode, that's the verb, telling the computer what to do, and then one or more addresses, those are the nouns, telling it where to find the data. And the control unit just repeats a simple cycle, over and over and over. Fetch an instruction, figure out what it means, and then do it. Let's make that a little more real. Imagine an instruction like add x, y. The opcode, the little code for add, might just be the number 1. The address for x could be mailbox number 99, and the address for y, mailbox 100. So the control unit fetches this, decodes it, and goes, okay, got it. I need to grab the numbers from mailboxes 99 and 100 and add them together. Simple as that. But here's the thing. The control unit doesn't actually do the math itself. It's the manager, right? not the mathematician. So once it decodes an instruction like add, it passes the actual numbers over to the arithmetic logic unit, or ALU. The ALU is the dedicated calculator. It's the part that does all the heavy lifting, the addition, the subtraction, and even the logical comparisons, like is this number bigger than that one? So we have memory to store stuff and a CPU to process it. But how does the computer actually, talk to us? Or to its long-term storage, like a hard drive? Well, that is the job of our final room, the input/output system, or I/O. Now, to really get the challenge here, we have to talk about speed. The CPU can grab data from RAM in about 50 nanoseconds. That's 50 times billionths of a second. It is just mind-bogglingly fast. But what about something like a mechanical hard drive? Well, that takes about, wait for it, 10 million nanoseconds to respond. I mean, to put that in perspective, that's like the super fast CPU asking for a book, and the librarian saying, sure, I'll have that for you in about 6 months. The CPU would spend almost all its time just waiting. And that, my friends, is a huge, huge problem. So the really clever solution to this is something called an I/O controller. Think of it as a special purpose processor that acts as a middleman. The CPU just tells the controller, hey, go get me that file from the hard drive. The controller then handles that whole slow process on its own, gathering up the data in a little holding area called a buffer. And this is the magic part. It frees up the main CPU to go work on other things. Then, when the controller finally has the data ready, it sends an interrupt signal. It's like tapping the CPU on the shoulder to say, hey, your data's ready. So we've toured the 4 rooms: memory, the control unit, the ALU, and I/O. But the true genius of the von Neumann architecture isn't just these separate components. It's one single revolutionary idea that ties them all together. This is it, right here, the stored program concept. You see, before this came along, programs were literally hardwired into the circuits of a machine. If you wanted to change the program, you had to get out your tools and physically rewire the computer. The von Neumann model proposed something totally radical. It asked, what if the program, that list of instructions, is treated just like any other piece of data? What if we could just load it into the same memory we use for everything else? And that is what makes your computer a computer. It's the reason your phone can be a calculator 1 second, a web browser the next, and then a camera the moment after that. By treating instructions as data, the machine becomes this universal tool that can be instantly reprogrammed to do basically anything, just by loading a new set of instructions into its memory. And that's the incredible, enduring power of this design. A simple blueprint, 4 rooms, and one big idea has powered the entire digital revolution for more than 75 years. Which leaves us with a pretty big question. What simple, powerful idea is going to define the next 75?